This is Frame by Frame episode 6, where today we'll be talking about the Hough transform. Now, the Hough transform is a feature extraction technique that allows us to identify different shapes in an image using computer vision. There's some of the applications you might be using this for are things like eyeballs or lines on the road or maybe even coins for a bank. This is an older technique that uses a more mathematical approach to things, and it was actually made back in the 1960s, but then it was modified for computer vision purposes in the 1970s. Getting into the actual technique, we're going to start with a Gaussian noise reduction filter to reduce any kind of noise that's going to be in the image, and then we're going to be using the canny edge detection process. So check out the last two videos if you haven't seen that already.
Yeah, man, just another night, just another day.
So if we look at a simplified example, we'll have an image here in what's called the image space, and that's your standard Euclidean distance between all the pixels, and you have a little bit of noise. We'll reduce that with some Gaussian noise reduction, and then we use the canny edge detection to be left with a simple edge right here. The Hough transform will introduce what's called the parameter space, parameters meaning variables like x and y. To use the parameter space, we're going to take a look at our image space where we have a straight line right here, which we can say as y equals mx plus b. We're going to rearrange the terms, we're going to solve for c, and we can plot that into our parameter space now. Each point that's on this line in the image space will be plotted into the parameter space. The catch is each point now is turning into a straight line in the parameter space. This line represents all the straight lines that will pass through the point xi, yi in this image space. We're now going to be repeating this process for each point that's on this line. So all the points will create a line that's crossing at the single point MC in the parameter space. Now this point is the true edge of the line in the image space. Even if we plot another point that's not on this line in the image space, it will plot a line in the parameter space that does not cross this MC point. So with multiple straight lines in the image, we may have several of these points in our parameter space. We can begin to see a pattern that's forming here where a point in the image space becomes a line in the parameter space, while a line in the image space will then become a point in parameter space. So with this relationship, we can algorithmically find the edges in the image just by looking at the parameter space. So after we plot all the lines into parameter space, we're going to be next using what's called an accumulator array. Now this accumulator array is just a quantified space where we'll identify the edges mathematically. So to start, we're going to set the whole array equal to 0, and we're going to tally or vote each time the line passes through it from the parameter space. So say we have an edge of an image in the image space along this line here. We plot this point, and then we'll show up in the accumulator array. So we'll plot another point, and the same thing will happen. And so notice how the center point has 2 votes now. We'll continue this voting process until all the points in the image are plotted, and then we'll identify the points with the most tallies. This process is repeated across the whole entire image, and we'll have several points that have the most amount of tallies, and then those will be the edges in our image. Another problem that may occur is when the line itself points up vertically and goes to infinity, then it becomes undefined. So to get around this problem, we're going to be using polar coordinates instead of the standard Cartesian graphs. I'm not going to dig too much into the polar coordinates, but the two things that we do need to know are rho and theta. Now, rho is the distance away from the origin that the line is, and theta is going to be the angle of the line with respect to the origin and the x-axis. The main advantage of using polar coordinates is that we can set the angle to be a finite from 0 to pi, and then we can also set the distance to be finite, which is literally going to be the distance of the actual image itself. Now, instead of taking a straight line into the parameter space, we're going to be taking the polar coordinates equation into the parameter space. Now, this is also going to plot a sinusoidal curve this time instead of just a straight line. The rest of the process is the same, where we'll just find where the points overlap each other, have the accumulator array go in, find the maximum value there, and then those values will be the actual edges in the image that we have. For identifying circles, we have the same exact process, except we change one thing. Instead of the linear line that we use in the image space, we're going to be using the equation of a circle, and then we're going to solve for a and b. A and b is just going to be the center points of the circle, and then rearrange the terms and put that into the parameter space this time. The Hough transform is one of the more complex algorithms that we can go through, and you can imagine how much more complex things will get when you have more intricate shapes that are involved instead of just circles and squares and straight lines. It's really great at identifying simple shapes like circles here in this example. The voting mechanism makes it a great option for images that have lots of noise despite having already passed through the Gaussian reduction filter. It's very customizable with a lot of different amount of parameters that you can change, and you can be tuned and even be capable of handling images that have incomplete shapes. On the flip side of this, the algorithm does need a lot of memory to keep track of all the outputs and the algorithm that's going on for the parameter space. Unfortunately, the algorithm does not work when the shapes are overlapping each other or may have not been well lit enough to be identified in the first place. With the Hough transform being a simplistic approach on paper, in reality it's not a great option if you're having more intricate shapes other than circles and squares and some straight lines. I'd like to shout out First Principles of Computer Vision for helping me out with this video today. Please check out their full in-depth video on YouTube.